need to go over. Okay. So today, in terms of reactions, there were a couple more reactions in the reading for alkene additions. And we'll see how far we get with those, as well as at some point either today or Monday we'll start defining the issue of regio and stereo selective. So if that doesn't quite make sense in the book, we will go over it either today or I didn't quite get to it this morning. So let's start with what's called hydroboration oxidation. So for hydroboration oxidation, we'll also do MER curation, DEMER curation. These are multiple step reactions. And they're not mechanisms that I'm going to ask you to reproduce. Like Wednesday. Wednesday I could ask you any of those mechanisms. These ones I'm not going to ask you to do, but I am going to show you so that you can kind of link together why we get the products we get from these mechanisms. So for hydroboration oxidation, you're going to add two reagents. You're going to add BH3 and then H2O2 hydrogen peroxide. What you're going to end up, the three questions are, what am I adding? And I'm going to end up adding an H and an OH. How am I going to add that? I am going to add that anti-Markovnikov. So in other words, what we saw on Wednesday was the hydrogen goes to the carbon in the double bond. With the most hydrogens, the other group goes to the other carbon. This is going to be reversed. And then this reaction goes 100% cis. So we need to explain, why is it anti-Markovnikov? Why is it cis? Okay. Now, bless you, the fact that it's cis means it doesn't undergo a carbocation intermediate. So, no. You can thank Hannah. So that's what we have to explain with the mechanism. So let's say I take a double bond and I'm going to add the BH3 to it first. Now there's a couple things about BH3 that are going to be new. And that is that the BH3 boron is one of those elements like aluminum that are more electronegative than hydrogen. Or sorry, hydrogen is more electronegative than boron. So that means the hydrogens are going to be delta minus and the boron is going to be delta plus. So we normally don't deal with minus or delta minus hydrogens, but in this case, this is our first example. So this is called borane. So this is borane and then hydrogen peroxide. Now what happens in this reaction is that I'm going to add the boron and the hydrogen to the double bond all in one step. So you can imagine me orienting the molecule maybe like this. And what will happen is, if the boron is delta positive, this pair of electrons will go to form a C boron group or bond. And then the BH bond will break, and basically you'll add a hydride to the middle carbon. Okay, so you're going to add both atoms at the same time. I'm breaking my boron hydrogen bond here. So the transition state for that is going to look something like this. We'd have a partial bond to the hydrogen, that hydrogen partially bonded to the boron, partially bonded to the CH2 group, and the double bond partially breaking. So this is going to be a square transition state. And there are no charges in this transition state, because our usual thing for transition states is we average the charges at the beginning, the reactant, and the product, there are going to be no species that have charges in either the reactant or the product. So there's no charges here. And so what happens is that I end up adding the hydrogen to the carbon number 2, and I end up adding the BH2 molecule to carbon number 1. So this is the first step in the mechanism. And this makes what's called an alkyl borane, is the name of it. So the second step in the mechanism is the peroxide. The hydrogen peroxide is going to come in and it's going to replace the BH2 with an OH in exactly the same spot that the BH2 was added. So this square transition state sets up the stereochemistry of 100% cis addition. You can't have a square transition state and have a hydrogen be, let's say, above the plane of the ring and the boron below the plane of the ring. There's not enough space for that to happen. So if this is your double bond, your boron's going to come in and it's going to plop right on top of it. It's going to add the boron and the hydrogen to the same side of the double bond. That's where the 100% cis stereochemistry comes into play. Assuming that the peroxide is going to replace the boron with an OH in exactly that position, which it will. Okay. So this is the reason for 100% cis, is this transition state. Okay. All right. Is everybody okay with that part? So then the issue is, what about what we're going to later on call regiochemistry? What about Markovnikov, anti-Markovnikov? Well, it turns out that you could end up adding the boron the other way. In other words, add the boron to the carbon with the most hydrogens and the hydrogen to the carbon. In other words, this would be this, if this ultimately becomes an OH, this one would be your Markovnikov product, would lead to your Markovnikov product. This one up here leads to your anti-Markovnikov product. And I already said that it's anti-Markovnikov, so this is going to be the way it adds. But the question is, why does it add that way and it doesn't add Markovnikov? Okay. And the reason that it doesn't add Markovnikov doesn't add Markovnikov but does add anti-Markovnikov is because of steric hindrance. It's going to be less sterically hindered to add the BH2 to the carbon in double bond with the most hydrogens. So the Markovnikov, anti-Markovnikov is because of steric hindrance. And the 100% cis is due to the square transition state of adding the boron and the hydrogen all at once. Now, the issue here is, if you look at this, you might say, but this is a pretty small group. So how is this that much more less sterically hindered than this one, so that you basically get like 100 to 0, that you get exclusively anti-Markovnikov? Because this step is not the only step in the mechanism. So we have 3 boron-hydrogen bonds that I can add to double bonds. So the stoichiometric ratio of this reaction is basically you need 1/3 of the number of moles of alkene for every 1 mole of boron. So I would take this molecule that I just wrote and it's going to react with another mole of alkene. So if I write that over here, I've got my CH3, CH2, I've got my CH, and this was the hydrogen that I added. I've got another CH2, and then I have my boron, but now my boron has another BH bond. That other BH bond could now add so that the CH2 of the double bond is going to add also to boron, so I could have this pair of electrons now go here and have this pair of electrons go there, so that now I can form a second equivalent of the borane. So that it looks like that. And the hydrogens I put in boxes are the hydrogens that are being added from the boron. Those are the hydrogens that are giving us our anti-Markovnikov regioselectivity. So then, this can happen a third time. So that ultimately what I end up making is I end up with the boron attached to 3 of those what were alkenes. Again, I'm not going to ask you to reproduce this mechanism. I'm trying to explain why we get anti-Markovnikov addition. I mean, this chapter would go a lot faster if I just said, here's a list of 12 reactions, memorize them. And then we could go on to chapter 13. But that kind of defeats the purpose. So now if I made the argument that it is less sterically hindered to add to carbon 1 up here versus adding to carbon 2 in the double bond, you can see that it's not just a single addition. It's the putting 3 alkyl groups around that boron. So when you put 3 alkyl groups around the boron, it's less sterically hindered to have them attached to the least substituted carbon in the double bond. Whereas if the boron was attached to the most substituted carbon, we would have the difference in steric hindrance multiplied by 3. So in this case, we have this is the reason why that boron adds anti-Markovnikov. Okay. So it's because the boron isn't just adding once, it's adding 3 times. Right, does that make sense? So that's step 1. Step 2 then is to replace the boron with OH. And that's what happens with the peroxide. So either way we write the mechanism, whether we say we've got CH3, CH2, a CH with our H here that we added, the CH2 with the BH2, or if we take the boron with 3 alkyl groups around it, when we treat this with hydrogen peroxide, I'm going to end up replacing the boron with an OH. And so now we have the addition overall of both reactions. We have H and OH adding to the double bond, anti-Markovnikov, 100% cis because of this mechanism. Right. Does that kind of make sense to everybody?
So just going back, you said you added the 4 to the least substituted carbon in the double bond?
Yes.
Just you're looking at only the 2 carbons.
Right. I'm looking at the 2 carbons that were involved in the double bond. The boron goes on the carbon that is least substituted. That's the carbon with the most hydrogens, although we could get into least hindered. They may have the same number of hydrogens, but one might be more hindered than the other. But we'll leave it at number of hydrogens to begin with. So the boron adds to the carbon that is least hindered, has the most hydrogens. The hydrogen adds to the carbon that is the more hindered, less number of hydrogens. Markovnikov's rule was we add the H to the carbon with the most hydrogens. In this case, that's opposite of that. That's why it's anti-Markovnikov. The 100% cis comes because of the square transition state. Now we wouldn't see the 100% cis stereochemistry in this example, right? Because I've got already. Well, I don't have any chiral centers, so I can't see the stereochemistry 100% cis unless I make molecules with chiral centers, and this one doesn't have any chiral centers.
So you said that the H adds to the carbon in the double bond with the least hydrogens here, and then vice versa for the boron?
Because this is anti-Markovnikov. So if we did a ring, and this is where we're going to see the cis, 100% cis or 100% trans. If I had that alkene, and I said let's react that with BH3, H2O2, we can write the product simply by remembering what I'm adding. So you could say I'm adding H and OH, anti-Markovnikov, 100% trans. So if you wanted to go directly to the product, what you would do is you would say, okay, I'm adding H and OH, anti-Markovnikov, Jacob. Sorry, 100% cis. Typo. A verbal typo. If I do that, you just have to correct me. So that means the hydrogen would add to this carbon and the OH would add to that carbon. So if I'm just writing the product, I'm going to write in my H and OH. Now I'm going to put in the bold and dashed wedges to indicate that the hydrogen did indeed add 100% cis. And then the methyl group goes on a bold wedge because that's what's left over. And then down here there would be a hydrogen on the bold wedge. So this would be the major product of the reaction. Does it matter whether you add the H and the OH on bold wedges or on dashed wedges? No, as long as they're cis. And as a matter of fact, in this case, the issue is we would get both of those products 50-50. Because if I have the double bond, there's nothing stopping from adding 50% on top and 50% on bottom. So we would get a 50-50 mixture of these two compounds. Which shouldn't be all that exciting because what's the relationship between those two molecules? Enantiomers, diastereomers, same meso compound. What's the relationship between those two molecules? Guess again. Guess again. The enantiomers. Everything builds, right? Somebody put on Piazza, they asked on Piazza, is the final going to be cumulative or just over new stuff? Cumulative. Because everything is building on everything else. So why did we do enantiomers, diastereomers, same meso? Because now we need to determine the relationships between the products in order to determine regio and stereo selectivity, which I haven't gotten to yet. In this case, what's the difference between the two chiral centers? They're both chiral centers are same or opposite. They're opposite. Right, they're opposite because hydrogen dashed, hydrogen bold, methyl bold. So I switched two groups once. So they have opposite configuration. Same thing's true for the bottom. So these are enantiomers. And when you're looking at organic reactions, now that we know about stereochemistry, and particularly since this week we did the yeast reduction experiment, so we were able to show that we formed an unequal mixture of enantiomers. The general rule in organic chemistry is if you want to make a chiral product, and chiral could mean 100% of one, 0% of the other, or an unequal mixture of enantiomers like we did this week. When you want to make a chiral product, you need to have a chiral reagent. So this week our chiral reagent was the enzymes in yeast, or like most biomolecules, they are in a particular handed form. And so being in that handed form, they induced a chirality in the product. Not 100%. I don't even know what percent yet until I get the stuff to measure it. But certainly, if everybody got positive, it was at least 51-49 of one enantiomer over another. So the rule in organic is if you want to make a chiral molecule, you need a chiral reagent. In this case, there are no chiral reagents, so we make a 50-50 racemic mixture. Now the other products, if the H and the OH added trans, that relationship is going to be, that's a diastereomer. So in this case, we're always going to make a 50-50 racemic mixture, unless we use a chiral reagent that's going to tip the scale one way or another. And that's the difficulty in making a chiral molecule, is you need the chiral template reactant in order to make that happen. Because if you're going to make a chiral drug, and next week in lab we're going to take the Aleve tablet with the naproxen sodium, which is chiral, sold in a chiral form. That Aleve tablet, the one form that you take that reduces pain and inflammation, that's what it does. That's a positive thing. The other form, the other enantiomer, has some liver toxicity issues, as you'll find out when you do the pre-lab assignment. So hopefully the ones I took this morning are not liver toxicity issues, but pain medications. So if it wasn't that way, they wouldn't be able to sell it, right? Because of all the bad drugs in the past that have one enantiomer doing a positive thing and the other one doing horrible things. So you can buy ibuprofen that's in one chiral form. It'll cure your headache in about 20 minutes versus a racemic mixture, which takes an hour. So in order to make those, they have two choices. They use a chiral template to make it, or they split them 50-50. They have to separate the 50-50 mixture. But the problem, and we didn't really get into this, the problem with that is if you have if you have enantiomers, what is their only physical property difference? Polarized light. That's not a separation technique. So how do you separate those components? Maybe we'll get to that by the end of the semester, but that's difficult. And then showing that you have 99.9999% pure product as opposed to, 97 in order to be able to sell it and to not have, everybody who takes an Aleve tablet destroying their liver or a little bit of damage. Right. So whenever we do these reactions and we end up with a chiral center, we're always making the racemic mixture. So in this case, these two would be the product. You only have to show one. Just either bold or dashed wedges, but the OH have to be added cis. But they also have to be added anti-Markovnikov. Okay. So that's hydroboration oxidation. HOH, anti-Markovnikov, 100% cis. Okay. So if you're making your table, you now have what? HX, H plus H2O, hydroboration oxidation. Okay. All right. Does that kind of make sense to everybody? Okay, so that's reaction number 1 for today. Again, I'm showing you the mechanism to try and explain what's going on. The second reaction is also going to add H and OH, but with different regiochemistries, meaning Markovnikov, anti-Markovnikov, and maybe a different stereochemistry. So this is called MER Curation, DEMER Curation. And so MER Curation, DEMER Curation, we're going to add a molecule called mercury acetate. And the acetate is the deprotonated form of acetic acid, which is the 2-carbon carboxylic acid. So there are 2 of these anions attached to a mercury 2+, so that it balances out. The demercuration part, well, you're going to add mercury acetate and water in step 1. In step 2, which is usually, there is a then written, so you add mercury acetate and water, do the reaction, then we're going to add sodium borohydride to this, NaBH4. Okay. And so the BH4 is going to replace the mercury with a hydrogen. Now, this mechanism is going to foreshadow something on Monday where we're going to add bromine to the double bond. So we'll talk, so whatever we have here left over, and we'll talk about bromine, they're going to be very similar. But here's what happens. Well, first, before what happens. So mercuration, demercuration adds an H and an OH to the double bond. It adds them by Markovnikov addition. It adds them 100% trans. So different mechanism. So how do we rationalize this? Number one, the 100% trans is kind of good because it gives us the ability to add H and OH trans. I know how to add H and OH cis. And from water and H plus last time, I know how to add H and OH 50-50. So we have different ways to add HOH to the double bond. This reaction, quite honestly, is not something that we might do in an academic lab. We would never do this in a pharmaceutical. mercury is a neurotoxin, and yeah, there's a whole debate about mercury in vaccines. Mercury was in vaccines. It's no longer in vaccines. It was quite a long time ago. It was used as a preservative, which is sort of the reason why you now hear about the controversy, and I'll just leave it at that, as controversy about whether, vaccines cause whatever they cause. That's a debate that sometimes has scientific evidence in it, sometimes it doesn't, but it's beyond the scope of this course. But there was mercury in vaccines a long time ago called thimerosal. So if the FDA is involved in this drug, right, and I'm not making it in a country with no FDA and then shipping it to the US super cheap, and that would include any drugs, pet drugs, the whole 9 yards, right, because you can get your pet drugs from foreign countries as well. They may or may not have standards in place. Again, a topic for another class. Mercury being a neurotoxin is something that if I was to design a synthesis of a drug, I'd never do, because I could never prove to the FDA or lawyers when the lawsuit comes about that I got every single atom of mercury out of my drug. I could come pretty close because the detection limits on mercury are super low, but they're not at the atom level. So you could never prove that you've gotten rid of all your heavy metals. So a lot of the reactions we learn that have toxic heavy metals really aren't done that much. Mercury is one of them. So it's a neurotoxin in Alice in Wonderland. The Mad Hatter. He's not mad angry, he's mad with neurogenital disease. Okay, might be a little crazy. Why? Because hatters made the brims of their hats stiff in the old days by taking mercury metal and rubbing it into their hats, into the felt to make it stiff. Therefore, they handle a lot of mercury. They breathed it in, they put it on their skin, because I'm sure they didn't have gloves back in the day. And so the hatters tended to become mad, right? Hence the novel. Or who knows? Maybe there's a place where that happens. Right? You go through the mirror, and then you die, because all the sugars that you would eat for energy and for food are now the opposite configuration through the mirror, and your body can't handle them because you can only metabolize one type of sugar. Jacob. Yeah, that's the debate. So there's actually an essay that you can assign people, and usually in biochemistry, not in organic chemistry, to say, what if Alice really did go through the mirror? What could she eat? What issues would she have? What enzymes, etc., are totally dependent on one and only one configuration? So that's the debate, and that's the research, and I will not assign you that paper. But that is the issue of biochemistry. It's what's called specificity, right? If all the sugar changed right now from one form to the other, we would not be able to metabolize it. So it's whether or not our enzymes change, whether that kind of cancel each other out, not quite sure. Okay. So mercury, bad. But it still will do an interesting reaction. And the interesting reaction it will do is I'll take the same alkene and I'm going to react it with the mercury acetate. So what's going to happen is I'm just going to write these acetates without writing the complete structure, I have 2 of them attached to the mercury. What will happen is that the pair of electrons will come over to bind the mercury or bond the mercury, and then one of the acetates gets kicked off. Now, mercury acetate is mercury 2 plus with 2 acetate minuses, so it's neutral. Once you kick off an acetate, you end up with a mercury acetate that overall has a positive 1 charge. Let's think of that positive 1 charge being the equivalent of H plus. And I like even better to think of it as the equivalent of E plus. Because when I do addition reactions to alkenes, the majority of the reactions are going to be to add an E plus to the double bond. So which carbon is the mercury going to add to? I don't know, let's find out. So let's add the mercury to carbon 1. And if I do that, that leaves the second carbon as a carbocation. Let's add the mercury to carbon 2. And that leaves the first carbon as a carbocation. So kind of deja vu back to Wednesday. Which one am I going to form? Am I going to form the top one or the bottom one in terms of the intermediate? What do we think? Top? Why? Because it's not primary, it's secondary. So we got a secondary carbocation and a primary carbocation. We will not form the primary carbocation. So the mercury will add Markovnikovly, you could say, but Markovnikov's rule says you add H to the carbon with the most H's. I'm going to broaden Markovnikov's rule. I'm going to say you add the E plus. You add the electrophile to the carbon with the most hydrogens because that's going to give you the most stable carbocation. So in this case, this is the carbocation I'm going to form. Okay, it's mercury acetate and water. So then I'm going to take the water and I'm going to add it to the carbocation. What am I going to make? I'm going to make the oxonium ion. I'm still going to have the mercury acetate attached. So now I'm going to make the oxonium ion. And then what's going to happen next? Lose H plus to give me the product. And so what I did was I added the mercury to the carbon with the most hydrogens, and I ended up with the OH added to the carbon with the least hydrogens. That's step 1. Okay. Then step 2 is, now let's go ahead and this part of the mechanism hopefully can make sense. The second part of the mechanism is beyond the scope of what we want to talk about. If I now add NaBH4 to this reagent, what's going to or this compound, the hydrogen is going to replace the mercury. So now I'm going to end up adding H to the first carbon. So that's all sodium borohydride does. Whatever position the mercury was in, that's where the H is going to end up. Just like with the hydroboration oxidation, the OH ended up wherever the boron was. Okay. So net result is I added H, OH, across the double bond, Markovnikov. Everybody with me? Okay. Except there's a problem. What? Well, that was going to be my next question. So if the mechanism happened the way that I wrote here, what would you expect the stereochemistry of the hydrogen and the OH group to be? Got to go back to Wednesday. Ultimately, my water's adding to what kind of intermediate? Carbocation. What happens when you have a carbocation intermediate? You always get (50-50) racemic. Well, 50-50. Let's just leave it at that. You always get 50-50. That is not 100% trans. So if the mechanism was to happen the way I showed you, you would not get 100% trans. You'd still get Markovnikov, which is what I'm illustrating here. But this is not completely correct. So, am I lying to you? Could. Probably take a couple class periods before somebody goes, wait, you're telling us stuff that's different in the book. Never tried that before? Probably do that when somebody's visiting me, watching me, and evaluating me. And they'll be like, he taught the class totally wrong. And nobody said anything. Genius. So what's the nuance in this reaction that's causing it to be 100% trans? Here's the nuance. The mercury ion is big enough to sit over top of both carbons in the double bond. So actually it's not bonded to just one carbon. It's bonded to both, and it makes this triangular intermediate. Okay. You might say, well, why? Because it's big enough to do that, number one. And you could say, doesn't that look like the transition state for a hydride shift or a methyl shift? It does, except that was a transition state. This is an intermediate. And so the transition state was kind of fleeting. The hydrogen didn't move over and stay there. This stays there. So it's big enough to do that, but from the carbon perspective, this carbon's like, well, why do I have to take all the positive charge? And the primary's like, well, because I'm not allowed to. It's like, well, who made that rule? You can take a little bit. And so that carbon takes a little bit because the mercury is going to sit over both of them. So in essence, those two carbons are sharing the positive charge. Now, it is a very unequal sharing because the primary cannot take a full positive charge. So it's going to take as little as possible. But the critical part is it's still a triangle, because here's what happens next. What happens next is the water comes in and it's going to add to one of those two carbons. we know which carbon it's going to add to, right? It's going to add to this one. Why? Because that's the final product we got. But when it adds, it has to add from underneath where the mercury was. So the water's going to add underneath, the mercury is going to slide over, and now the water, which is going to become OH, the mercury, which is going to become H, are 100% trans. So this triangular intermediate is going to give us 100% trans. And any triangular intermediate, and we'll do one more of these on Monday, any triangular intermediate will always give 100% trans, because when you have the triangle, the other group has to add from underneath. Now, the reason that I did the mechanism the first time without the triangle was because you know we have to add the CH there. But what we need to do is we need to interpret why it adds there in the triangle, because we're going to need to do that when we add a bromine there on Monday. So we'll have to interpret our mechanism in terms of the triangular intermediate, and we'll do that on Monday. Okay. So that's why it's 100% trans.
So for MER Curation, demercuration, we haven't really done a problem for it yet. We're just kind of exploring the mechanism.
Sure.
And we don't need to know the mechanism?
No. Because the mechanism we're going to do on Monday with the bromine is going to be exactly like this, and that one I will expect you to know. Okay, the reason I stopped early was right, never lose a chance to review. Sadly, a former colleague of mine one time ended class like 10 minutes early when somebody was observing. That didn't go well, sadly. So we never stop early just to stop early. But here's the part of the take-home quiz, or the practice quiz, practice problem that people have been having the most difficulty with, at least when I graded it this morning, and I suspect problems are all the same. So the question here is, for this reaction, I have hydrogen A, hydrogen B, and hydrogen C with my tertiary butoxide. Now, I did upload, somebody asked about how you start this problem on Piazza. I thought the answer was really good. I gave it a good answer, check mark. But before I even saw that answer, I was thinking about sort of flow charting this, trying to. So on Piazza, there's kind of a flow chart that I kind of devised. If you look at the flow chart and you're more confused, forget about the flow chart. Okay? But these are the steps that you go through, which were outlined in that answer. So number one, we need to find all the beta hydrogens, which I've just done, HA, HB, HC. Then the question is, because it's tertiary butoxide, it has to be E2. So the stereochemical restriction on those beta hydrogens is they must be trans in the ring or become anti-periplanar outside of the ring. So any beta hydrogen outside the ring can always become anti-periplanar. So if you have a beta hydrogen outside the ring, it will always be deprotonated in E2. But really the question is, can I remove HA in this reaction? No. Why not? It's cis to the leaving group. So I cannot remove HA. Can I remove HC? Yes. So that means that I have two possible products in this reaction. I have the double bond outside of the ring, and I have the double bond inside the ring from the removal of HC. So these are my two possible products. Which one is the major product? Well, that's going to depend on the base. If it's NH2 minus, the major product is going to be the most substituted double bond. If it's tertiary butoxide, the major product's going to be removing the beta hydrogen that is least sterically hindered. So of HB and HC, which one is least sterically hindered? HB, because it is what kind of hydrogen? Secondary, and HC is tertiary. Okay. So as we do as you do those problems, you want to think about that sort of series of steps. All the possible products you can get come from E1. But then when you're doing E2, you have to sort of shave those down because only the ones that are trans can be formed. Okay. All right, so that was the problem that people had the most difficulty with. Back in one of the folders, there's a bunch of multiple choice problems. There was an answer key. I did put up a narrated answer key the other day for those. But if you have questions on this, put them on Piazza and I can answer them. But this is the one that caused most people problems. Okay, I will put the video up for Monday as well as the reading assignment. And if you have any questions on any of that, email or put it on Piazza and I will answer it over the weekend. I'll take your graded practice problems up here